put that. So y double prime terms first. So it is 4b e to the negative 2t my negative 4c cosine 2t minus 4d sine 2t. So that is the y prime term. Now we're going to go with the first derivative term. So minus, you're going to get negative 2b e to the negative 2t negative 2c sine 2t plus 2d cosine 2t, and then the y term, which is negative 2 times the y term, which is a, that's the longest term, 2e negative 2t plus c cosine 2t plus d sine 2t, which is equals to the ft, which is 6 plus 8 minus 2t minus 4 cosine 2t. Good. So that's the expression we get. Now what we're going to do, we're going to equate the coefficients of linearly independent terms. So what are the linearly independent terms you can see here? We have a constant, which is a linearly independent term. And then we have exponential function, which is linearly independent. We have sine, which is linearly independent. We have cosine, which is also linearly independent. So those are the 4 terms that we have here, which are linearly independent. So step 5, equate coefficients of linearly independent terms. So we'll start with the first term. We'll start with the constant term. So let's start with the constant term. What are the constant terms we have? You're going to see a is a constant, and that's the only term we have. And then other side 6. So we're going to equate those two. So we have negative 2a equals 6. This directly going to give a. A has to be negative 3. So we all know the a value. Same thing. Let's go to exponential function next. So e to the negative 2t. So we equate the coefficient of that. That's also linear independent term. So let's start with that. So you can see we have that e to the negative 2t, and then we have this one, and we have that one, and on the other side we have this. So those are the 4 terms that we have. So 3 on this side, 3 on the other side. So we have 4b, and then we have negative negative positive 2b, and then we have negative 2b, good, and then equal on the other side we have 8. So how this simplifies, you can see this and that get cancelled, so you will get 4b equal 8. In other words, b equal 2. So we already know a, we already know b. Now the only thing that we need to do is find the coefficient of sine and cosine. So let's go with one of them. So let's go with cosine 2t, because they are also linearly independent. So if you go with that, we have cosine term here, we have cosine term there, and then this. Those are the 4 terms. So let's go with one by one. So the first one is negative 4c. The next one is negative 2d. The next one is negative 2c. Those are all the terms on the left side equal the right side negative 4. See whether you can simplify this a little. So you can see negative 4c, negative 6c, so negative 6c minus 2d equal negative 4. What we can do is we can divide this one by negative 2. If we divide this one by negative 2, you're going to get equation 3c plus d equal 2. So I'm going to call this equation number 1. Now what we can do, we're going to create a similar equation for sine 2t and solve the 2. So let's see what you're going to get for sine. For sine, we have sine 2t, we're going to get negative 4d and then plus 2c minus 2d equals 0, but there's no sign term on the side. This simplifies to negative 6d plus 2c equals 0, and if you divide this by, okay, I'm going to write it here. So this is going to give you negative 6d plus 2c equals 0. If you divide by 2, you're going to get c minus 3d equals 0. I'm going to call this equation number 2. Now what we're trying to do, we can simply get rid of d term by, so I'm going to multiply the first equation by 3 and add to the second equation. When you do that, you're going to get 9c plus c minus plus 3d minus 3d, which is equal to 6, and you can see this gets cancelled out, so you will get the value of c. So 10c equals 6. It says that c equals 6 over 10, in other words 3 over 5. And then we can use the second equation. So d is 1/3 of that, so this says that d equals 1/3 of c, which is 1/5. So we find the two values. Now we can write the general solution. So thus the yp, or the general solution, yp is negative 3 plus 2 e to the negative 2t plus 3/5 cosine 2t plus 1/5 sine 2t. So we get all the terms. Now what we can do, we can write the general solution. So number 6, the general solution. So the general solution is y equal yc plus yp. So you can substitute is c1 e to the minus t plus c2 e to the 2t and then minus 3, let's add them, plus 2e minus 2t plus 3/5 cosine 2t plus 1/5 sine 2t. So in the exam, like, you know, you're not going to get a question like this long, but here I'm telling you, like, you can manage all of them together, but you will get like 1 or 2 terms, not like a lot like that. Okay, now the last step is, now we can use the initial condition to find c1 and c2. So you can see that the only thing that we don't know is c1 and c2. To find that, we can use the initial conditions. So initial conditions we use at the end. That's what you remember. So the step 7, using the initial conditions, we have y0. So 0, which is y0. That means you plug in 0 for all the t's. So you're gonna get. So what are you gonna get? So let's write a separate equation for that. Yeah, I'm gonna write it like that. It's much easier like that. Using initial condition y0 equals 0, we have 0 equals c1 plus c2 minus 3 plus 2e0 plus 3/5 cosine 0 plus 1/5 sine 0. Now we know that sine 0 is 0, cosine 0 is 1, e0 is also 1. So this is going to give you an equation. So what equation you're going to get? You're going to get 0 equals c1 plus c2. C2 we have what do we have? We have minus 3 and also we have minus 3, and we have 2 here, so it's a minus 1 plus 3/5, that means minus 2/5. That's what you get. So I'm going to call this equation number 3 because we already have 1 and 2. Now the same thing, let's try to use the other conditions. So we get one result here. Now first we take in derivatives, first. We're going to get y prime t equals to negative c1 e to the negative t plus 2c2 e to the 2t minus 0 minus 4 e negative 2t minus 6/5 sine 2t plus 2/5 cosine 2t. And now what we're going to do, we're going to use the condition using y prime 0 equal to, we're going to get this equals to negative c1 plus 2c2 minus 4, and then negative 6/5 sine is 0, so that's gone, plus 2/5 cosine 0. Okay, so if you plug in the values, because again this is 0 and this is 1, you're gonna get if you move negative to the other side, 6 equal negative c1 plus 2c2 plus 2/5. I'm going to call this equation number 4. Now what we can do, we can add them. Once you add them, this can cancel out, you get c2. So let's do that. And also, you see this is negative, this is positive, they cancel out also. So that's interesting. So by 1 plus 2, we have 6 equal 3c2. In other words, c2 equal 2. And then you can use one of those equations. So let's say c1, if you use the first equation, c1 equal negative c2 plus 2/5, and we can plug in, so it's negative 2 plus 2/5 equal negative 8/5. So we get the solution. So therefore we have the solution y as negative 8/5 e to the negative t plus 2e to t minus 3 plus 2e negative 2t, and then 3/5 cosine 2t plus 1/5 sine 2t. You can see that none of the terms are 0. That's very interesting. Okay, so that's the solution. So it's just like a writing few terms, but otherwise it's not that difficult. But you want to make sure that you kind of follow the pattern, guess the proper YP term, and then after you get the general solution. So you can see the most lengthiest part was to find C1, C2. Otherwise the problem was not that difficult. The finding C1, C2 takes time because of a lot of terms. But if I say find a general solution, it won't be a very difficult problem. Okay? Yeah. Let's expect something like that. Good. So the next topic is the variation of parameters, and that's the last one we're going to talk about in this this part of the review. In the next one, we're going to talk about the series solution, Laplace transform, and the system of equations. So the only thing we're going to discuss in this one is the variation of parameters, but that's the easy one because you are allowed to use the formula. So I'm going to discuss the formula and the technique. So let's talk about that. So let's talk about the last topic, the variation of parameters method. So this is 22. the variation of parameters, variation of parameters method. We know that the undetermined coefficient method only works for 3 cases. So the problem is, what if you have something else? So we can use variation of parameters in those cases. So this is a little bit more powerful than the undetermined coefficient problem. So why we use this one? We use this one to find yp, the particular solution of y double prime plus px y prime plus qxy equal fx. So it's the same problem, but it has to be in this form. So we write that standard form. Okay, if it is not in the standard form, you have to bring it to standard form first. So these are the steps. So let's go with the steps. So the first one, find two linearly independent solutions. Find two linearly independent solutions of the homogeneous equation y double prime plus px y prime plus qxy. So we have to solve this first. So it can be constant coefficient or maybe Cauchy-Euler. So that's the first thing. And then also the px and qx may be, need not, may be constants. Okay, so that's the first step. You find two solutions. So let them be linearly independent. And let them be y1 and y2. So let's call those two solutions of y1 and y2. Those are the solutions of the complementary equation, the homogeneous equation. Now what we're going to do, we're going to guess the solution. So guess, so it's the extension of the reduction order. Guess yp of the form, guess yp of the form yp equal u1 y1 plus u2 y2. So for the non-homogeneous, we have one other term. If you have the homogeneous, it's only u1 y1. But when you have non-homogeneous, we add one more term. So the goal is to find this u1 and u2. So that's the goal. How to find this u1 and u2. So we do a very similar thing. We take the derivatives and plug in to the equation and get two equations to solve for u1 and u2. So you can see where u1 and u2 are unknown functions. Where u1 and u2 are unknown functions. So we need to find those two. Okay, so the goal is to find u1 and u2. So what's going to happen when you plug in? You're going to get. So I will skip the other part. So we're going to end up with these two equations. So we're going to solve the two equations. Solve the two equations. Solve the two equations. Solve the two equations to find u1 and u2. What two equations? These two. It is u1 prime y1 plus u2 prime y2 equals 0. That's one equation. The other equation is u1 prime y1 prime as well plus u2 prime y2 prime equal the function fx. So we can solve these two equations. That's always the case. You're going to end up with these two equations. So the goal is to solve these two equations and find u1 and u2, and then after you find u1 and u2, you're going to plug in there, you get yp. So that's how you find the solution. So let's use this method to solve a problem like that you cannot do using the undetermined coefficient method. So let's see this problem. So example, find the general solution of general solution of y double prime plus y equal tan x. So if you have this equation, you cannot do you cannot solve this using undetermined coefficient because tan doesn't work. So the problem, so what we try to do is just try to find the two linearly independent solutions of the homogeneous equation. So that we can do very easily. The characteristic equation of y double prime plus y equals 0 is lambda squared plus 1 equals 0. So lambda equal plus or minus I, which you can write as 0 plus or minus I. So thus, using the constant coefficient argument, you don't get the exponential term, you only get the sine cosine terms. So that means yc has the form c1 cosine x plus c2 sine x. Now what we can do, we're going to pick these two functions as y1 and y2. The order doesn't matter. So let y1 equal cosine x and y2 equal sine x. So let's pick those two functions. Now what we can do is, now we're gonna so suppose or assume yp of the form u1 y1 plus u2 y2. In this case it is u1 cosine x plus u2 sine x. Now we can take derivatives. Then from the equations, the two equations, we're going to get u1 prime cosine x plus u2 prime sine x equals 0 as the first equation. The second equation says u1 prime, take the derivative. So once you take the derivative of cosine, it is negative sine, so it is negative sine x plus u2 prime cosine x. We take the derivative, which is equals to whatever on the other side, so in this case tan x. So those are the two equations that we need to solve, 1 and 2. Now we're gonna think of how to solve. We're gonna use the elimination type of argument. You can see you can eliminate u1 term easily. What we can do, we're gonna multiply by the missing term and add them, it's gonna go away. So that's the kind of idea. So let's do that. So simply by, we're going to multiply the first equation by sine, the second equation by cosine, because those are the missing term. We're going to multiply these two and add them, so you're going to go away. So by 1 times sine x plus 2 times cosine x. If you do that, when you add them, this is going to go away. On the other side, what will happen? You're going to get u2 prime sine squared x plus u2 prime cosine squared x equal, so the bottom one you multiply by cosine, so it is tan x times cosine x, which is, what is it, tan means sine, cosine, so sine x, so which is equal to sine x if you simplify. And here what's going to happen, you can see this is 1, so you're going to get simply u2 prime, this is sine squared x plus cosine squared x, which is equal to sine x, but this is 1, so this implies u2 prime equal sine x. That's all you get. Now what you can do, you take the integral, you get u2. So if you integrate, so u2 is simply the integral of u2 prime dx. So that means you just integrate that. So that is sine x dx. That means negative cosine x. So that is u2. Now by 1, you have u1 prime cosine x plus u2 prime sine x. So if you plug in, you're going to get u1 prime cosine x plus sine x, that's the derivative of negative cosine, times sine x, which is equals to 0, that's how it says. Now if you look at the last equation, the last part, which says that u1 prime is sine squared, so negative sine squared divided by cosine x. That's what you get. Now what we can do, we have to think of how to integrate this one. So what we can do is, we can write the top as cosine squared x minus 1 over cosine x, which you can split as cosine x minus 1 over cosine means secant x. So that means it's very easy to integrate. So u1 is the integral of u1 prime dx. So let's integrate the two separately. So cosine x dx minus the secant x dx. And we know the cosine. Cosine means the sine x. That's the easy part. And then so we have minus. We know that the secant means natural log secant tan, secant x plus tan x. That's the formula from Calc 2. We are going to add c, so Calc 2. Okay, so that's a formula. We know the secant integral of secant is ln secant tan. That's a formula. Okay, so now we have that. So that means we can write the solution now. So the yp is simply u1 y1 plus u2 y2, which is equals to cosine x times sine x minus ln secant x plus tan x plus u2. U2 means negative cosine, so it is sine x times negative cosine. Now you can see that this and that get cancelled, so you only get the last term. So that means the yp is negative cosine x ln secant x plus tan x. So the general solution is y equal yc plus yp, c1 cosine x plus c2 sine x minus cosine x ln secant x plus tan x. Okay, so that is the general solution, which has two constants c1 and c2. Good. So that's the kind of idea how to use the variation of parameters method. You're going to write the two equations for u1 and u2, and this use the elimination method to remove one of them and solve for one, and then use one of those equations again to solve for the other one. The variation of parameters also has a formula, so let's discuss that, and you are allowed to use that in an exam. So let's talk about the variation of parameters formula. So formula for variation of parameters. Variation of parameters method. So let's talk about that. Again, the same idea. Let's say two linearly independent solutions, two independent solutions of y double prime plus px y prime plus qx y equals 0 are, let's say, y1 and y2. That's always the first step. We find two linearly independent solutions of the standard equation, and then the particular solution is given by a particular solution of y double prime plus px y prime plus qxy equal fx is given by p equal, it is simply u2 y2 y1 fx over the Wronskian y1 y2 order matters minus y1 y2 fx over the same Wronskian y1 y2 dx. So you can remember this formula and use when there is a variation of parameters type of problem, because there are a lot of problems that you can use the undetermined coefficient method, but this works. Only problem is whether this integral can be done, because sometimes what happen, this is not going to work. Okay, sometimes it's even difficult. So this is simply the Wronskian. Now you know that why the solution has to be linearly independent, otherwise the Wronskian can be 0. So we make sure that it's not equal to 0 because we divide by that. Okay, let's just do one example from that just to see how it works. And then that is the end of the review too. So let's do this problem. So let's say use the variation of parameters method, to find the general solution of this equation y double prime minus 2y prime plus y equal ex over x to the fourth. You can see that this one you cannot do using the undetermined coefficient method. See the format, because there's something in the denominator, so then you cannot do it. So when you take the derivatives, you're going to powers get more and more and more, so it's not going to work. Okay, so let's use the variation of parameters. So the answer, so first we can look at the characteristic equation, the homogeneous equation. So the characteristic equation of the homogeneous equation is lambda squared minus 2 lambda plus 1 equals 0. The zeros are you can see it is a lambda minus 1 squared, so that means lambda equal 1 1. That's a repeated solution. So thus the yc is c1 plus c2 x ex, or in other words c1 ex plus c2 x ex. So that means those two are the y1 and y2, the two solutions, y1 y2. So so take or pick or select y1 equal ex and y2 equal x ex as 2 independent solutions. Independent solutions. Now the Wronskian W y1 y2, so y1 first, y1 y2 y1 prime y2 prime. So if you plug in, you get ex ex, that means ex plus xex. If you multiply through, you get ex times ex plus xex minus x times ex. So you can see this and that get cancelled out. So you get e to the 2x, which is not equal to 0. Perfect. Okay, so that's the Wronskian. Now the solution. So the particular solution is by the formula, it is yp equal y2 y1 fx over the Wronskian y1 y2 in that order minus y1 y2 fx over w y1 y2 in that order. So same thing, no change, but with a negative sign in between. So let's plug in. So if you plug in, you're gonna get x ex, that's y1, and then we have ex over x to the 4th power over Wronskian, which is e to the 2x dx minus y1, that is ex. We have what we have, xex, again ex over x to the 4th over e to the 2x dx, and you can see there are a lot of cancellation going on. This cancels with that, the same thing happens on the other side. So you simply end up getting xex, the integral of 1 over x to the 4th dx minus ex times the integral of 1 over x to the cube. So these are very easy to integrate. So if you integrate them, you get xex times x to the negative 3 over negative 3 negative ex times x to the negative 2 over negative 2. If you simplify, you get, what do you get? Negative ex over 3x squared plus ex over 2x squared. If you add them, you get ex over 6x squared. Okay, that's the yp. Now what you do, you write the general solution. So the general solution, y equal the sum of the two, yc plus yp. Yc is what? Which is c1 ex plus c2 xex plus ex over 6x squared. So that is the general solution using the formula. So it's not long, but you need to simplify the integral. This is the end of the review 2. So next we can talk about review. In review 3, we can talk about the series solution, at least 2 examples, and the Laplace transform and the eigenvectors method. This is the part 3 of the final exam review of the differential equation class. In this review, we're going to talk about 3 topics. The first one is the series solution method. We will discuss 2 problems, first order and second order. And then we're going to go to Laplace transform method. So we will go with the definition, and then how to solve a differential equation, and the convolution, and the Heaviside function or the Switchy functions, and then the Dirac delta functions. And then finally we're going to talk about the solving a system of ODE. So we will go through the 3 techniques, the elimination method, and then the Laplace transform method, and the eigenvectors method. So let's start with the series solution method. So it is number 23, the series solution method. Series solution method. So this is a kind of a last resort type of situation, because there are a lot of differential equations you cannot find closed form solutions. So in that case, what we're going to do, we're going to assume a series solution. We assume there's a solution given as a power series, and then we try to find the coefficients of that. And once you know the coefficients, you pretty much know the solution. So that's the kind of idea. So we normally deal with second order differential equation in this course mainly. So we have a equation like this. So ax, let's say y double prime plus bx y prime plus cx y equals 0. So let's say it's a homogeneous equation. So what we're going to do, we're going to assume, so the first step, we're going to assume a solution of the form, y equal sigma n going from 0 to infinity Cnxn. So we assume that the solution can be written in this form, and then after we do that, we're going to assumption, and then we can take the derivatives of this one. So we're going to take derivatives. So depending on the differential equation, if it's a first order, you need 1 derivative. If it's a second order, you can need 2 derivatives. So take derivatives. That's the second step, and plug in. So we take the derivatives and plug into the equation, and plug in to the equation. So we can take the derivatives of the series and then plug into the equations. So we have 2 steps. So take the derivative and plug into the equation. Third one is, after you plug into the equation, we try to find a relation between the coefficients. So we can try to find the relation among the coefficients. Okay, so find a relation, among coefficients. Okay, find a relation, we can say between coefficients. So it will be clear what we mean by that, because sometimes you can express like what we try and do, we can try to find a solution for Cn plus 1 or Cn in terms of other coefficients. Okay, that's a relation. We find a relation between the coefficients, and then what we can do, we can evaluate few coefficients. So after that, we can do find C naught. We can probably have it. So then we're going to find the rest. So we're going to calculate few, and if possible, that we don't know, if possible, we can say, if possible, find a formula for Cn or Cn plus 1. Normally Cn plus 1. So we try to find a formula, but that sometimes is impossible. Like, I mean, you can, but it's going to be like very complicated. After that, what we can do, we're going to plug in them and then write the solution. And then after we do that, then we can write the solution. Write y, which is sigma n going from 0 to infinity. We're going to plug in here. So Cn xn So like, so if you look at the expanded versions like that, so we can just plug in for the coefficients because that's what we found earlier. So we're gonna plug in here. So that's the kind of point. So we do that, and sometimes we can see a pattern and find a closed form solution, but that's not always the case. So find a closed form solution. Again, if possible. So that's not always guaranteed. Okay, these are the kind of steps to do a problem. So let's look at a problem and see how it's gonna work. So we can start with the first order equation. So let's say, so example, find a series solution. Find a series solution. Find a series solution of y prime plus 3y equals 0. So we're going to try to kind of find a solution for that. Y prime plus 3y equals 0. Again, we're just going to follow the steps. So the steps are, I'm going to assume y equal a series solution. So y is given as a series. So that's the assumption. We assume that. Now what we can do then, we can take the derivatives. So you can see that when you take the derivatives, the first term is a constant. So when you take the derivative, what will happen? The first term disappear because it's a constant. So that means we can start with y prime, which actually start with n equal 1 because the constant term goes away. So we just take the derivative. So if you take the derivative xn, that means n cn x, you subtract 1. So that's the derivative. And you can see that the important thing, start with 1 because the constant term disappear. So if you take one more derivative, it's going to start with n equal 2 because now the first term is a constant. So if you take the second derivative, it's going to go away. So that's something we need to remember. Okay, good. Now what we can do, substitute. So we can substitute. So once we substitute, what will happen is y prime plus 3y equals 0. So that means you're going to get y prime. That means n equal 1 to infinity n cn xn minus 1 plus 3 times y. Y means n going from 0 to infinity cn xn, which is equal to 0 on the other side. Okay, so we plug in. So that step is over. We plug in. We take the derivatives and then plug in. Now what we're going to do, you can see that we check what terms we're going to get. So for example, let's plug in the first value in the index. So you can see for the first series, the first value is n equals 0. So you plug n equals 0, first value is n equal 1. If you plug n equal 1, you get x to the 1 minus 1 means x to the 0. So you get x to the 0th power in the first one. Second one, you can see the index value is n equals 0. When you plug in n equals 0, you get x 0. So that means that's a good one. That means you get the exact same number in both. But if you do not get the exact same number, we need to write the uncommon terms first. We can write the uncommon terms and then start writing the common terms. So that's what we're going to see in the next example. But here you can see everything start with x0. So everything looks great. Now what we're going to do, we're going to use the seesaw method. Remember the seesaw method? So we're going to use the seesaw method to reindex. I'm going to write it here. So next what we do, use the seesaw method. So seesaw method to reindex. So what's the seesaw method? It's a method that I introduced. So you can find them in other books. Okay, so you can look at the video about seesaw method. It's there. So what we can do, it's very simple. Because you can see in the second sum, it is xn. We try to get the xn in the other one as well. How to get xn? You can see to get xn, you have to increase the index by 1. So you can increase this one by 1. What we do, we increase inside, decrease outside. That's what we call the seesaw, because if one goes up, the other goes down. So that's the kind of idea. So it's like a seesaw. So this side goes up, then this side goes down, so that this stays the same. You see that the middle never change, but one goes up, one goes down. So that's the kind of idea here. When one goes up, the other goes down. So that's what we call the seesaw method. So it's very simple. It's going to make the calculation much easier. So if you use that, so outside you can increase by decrease by 1. That means your sigma going to start with 0 because you go down by 1. And inside you can increase everything by 1. That means n become n plus 1, n becomes cn plus 1, x is n minus 1. If you add 1, it becomes xn. Perfect. And then here I'm going to bring the 3 inside. So this is 3cnxn. Now you can see that both have the exact same index, exact same power xn, and exact same index. That means you can combine. So we'll combine them into 1. So we can write this one as sigma n going from 0 to infinity, n plus 1 cn plus 1. I'm not going to write the xn term, leave it. And then from the other one you get 3 cn. Now we can write the common xn outside. So now what this says? This says that the whole series equal to 0. The only way this can happen is this term has to be 0, because there's no other way that the whole series is 0. So that means this implies that this term, the coefficient, is 0. And that's exactly what we need. So let's write that. So we're going to get that n plus 1 cn plus 1 plus 3cn equals 0 for the index value. Index values are starting with, you can see 0, 1, 2, like that. So it's always coming from the sigma. Whatever the value, you're going to put it there. Now we can solve for cn plus 1. So cn plus 1 is, if you move to the other side, is negative 3 over n plus 1 times cn. So that is the relation. That is actually the relationship between the coefficients. Okay, so you find a relation. Again, this is only valid for n going from 1 to 3, like that. It's only valid for those. Now what you can do? Just calculate few values. Okay, so we can start with this first value, n equals 0. So if n equals 0, you're going to get c1. Let's plug in. Just plug in n equals 0. So you're going to get negative 3 1. So it's negative 3 c naught. That's what you get. Now we're going to plug in n equal 1. If you plug in n equal 1, you're going to get c2 is become minus. If you plug n equal 1, you get 3 halves c1. But we already know what is c1. So let's plug in the c1 value. When you plug in the c1 value, what happen is you get negative 3. You multiply by another negative 3. That means negative 3 squared. We leave it like that. And in the bottom, you get 2 c naught. So that's what you get for the second coefficient. And then go with n equal 3. So keep writing until you see a pattern. So if you plug n equal 3, what happens is still negative 3. If you plug in 3, this become so if when you plug in 1, you get 2. When you plug in, oh, actually I missed the value. This n equals 2. If you plug n equal 2, then you get that, and then this become 3 c2. Now we know c2, so we can find the c2 value here. So when you plug the c2 value, because c2 comes from the previous step, you can see you get another negative 3. So I'm going to write it like that over 3 times 2 here, c naught. So, and then you can see that what happened every time you're going to multiply by the same index like that. You just divide by that. So that term comes extra. That's gonna you add it to the previous one. So that's what you see. So that means if you want to keep going like that, so at the nth step, what's going to happen? You're going to get n. So let's say in minus 1 step. If you go in minus 1 step, you're going to get cn equal minus 3 over n. Here it is cn minus 1. That you can simplify, you can substitute. So what will happen when you substitute like that? You're going to see that it is negative 3. So you can see that when you have 1, it is negative 3, only one of them. When you have 2, there are 2. When you have 3, 3. So that means in this case you're going to get n of n. In the bottom, you can see that also that number exactly matches the bottom number. So that means in the bottom you're going to get n times n minus 1 times like that. That's simply the factorial. So times c naught. So if you go back, what you have gain is negative. So if you go back and you can fill this now because you see the pattern now. So it is negative 3 squared factorial 2 c naught. This become negative 3 cube over factorial 3. Now this is negative 3 to the n over factorial n c naught. So that's what you get. So that is the general coefficient. Now what we're going to do, we're going to plug in that in the equation. So we found the coefficient. So let's plug in. So therefore, or then you can see y, which is sigma n going from 0 to infinity, cn xn. So if you plug in for cn, you're going to get it is negative 3 to the nth power over factorial n, and then I can write the c naught outside. So xn, I'm going to write the c naught outside. But that's kind of make it simple. So it is equal c naught. I write c naught outside is common. So what is going on here? So you can see this is simply c naught times n going from 0 to infinity. You can write this one as negative 3x to the nth power if you combine. If you now, what is this? So you can see this is simply the Taylor series of e to the negative 3x. So this is simply c naught e to the negative 3x as expected, because we know that this differential equation is one of the 4 fundamental equations. We already know the solution. It is c naught e to the kx. In this case, k is negative 3. That's exactly. So we exactly get that. So if you forgot what I'm writing here, we know this formula. So e to the x is sigma n going from 0 to infinity xn over factorial n. And you can see that's exactly what we have here. Here x is negative 3x. So that means you get negative 3x like that. So this is the solution of the differential equation, and you can see that's not that difficult. After you find the relation, try to evaluate few and see whether you can find a pattern. And if you can find a pattern, you can nicely simplify like that. So yeah, so that's about that. So I'm going to do one more example from a little like a higher, like second order differential equation. So let's do a little complicated one just to see what we can do. But in the exam, the question is going to be reasonable. So you will get a reasonable question. But here I'm going to do like question just to see what's going to happen. Okay, so this is like a 3-term differential equation, 3-term. Good. So let's do that. So the next example, again, find a series solution. Find a series solution of. Find a series solution of x minus 1 y double prime minus x y prime plus y equals 0. So that is the differential equation we're going to solve. The same idea, but this is second order. So it doesn't really matter. So but only thing is we need to take 2 derivatives. So the answer. So we're going to say assume a solution of the form, assume a solution of the form y equal sigma n going from 0 to infinity cn xn. This step is always the same. Now we take the derivative. As we discussed, once you take the derivative, you can see you can start with n equal 1 because the first term goes away. So you get n cn xn minus 1. Take one more derivative. So you're going to get the new first term going to go away because that's a constant. So you're going to start with n equal 2. And then you have one more. So it's n minus 1 cn, no change, x to the n minus 2 now. Okay, so there are 2 things to focus on, this and that, here this and that. Good. So those are derivative. Now what we can do, we can plug in. So substitute into the equation. So substitute into the equation. So if you substitute, what we get? We have x minus 1 as a term, and then y double prime. So that means the sigma n going from 2 to infinity n minus 1 cn x n minus 2, then minus x, the first derivative, which can start with n going from 1 to infinity, 1 to infinity n cn x n minus 1 plus y, which is sigma n going from 0 to infinity cn xn. So we write that. So the next step is we try to bring this inside before we change the index. Okay, we're going to multiply through. So let's multiply through. If you multiply through, what will happen? You can see there's x term. Once you multiply by x term, inside it's going to be x to the n minus 1. And then there's a minus 1 in front. The minus 1 multiplied by the, so we can start with that. So that means the first term going to be now. That's the highest one, so we're going to go with that. So it is minus sign go inside n minus 1 cn x n minus 2, because I multiply by the minus 1. And then let's start multiply with x. When you multiply with x, you get it's still n going from 2 to infinity, no changes with the index. n minus 1 cn x. When you multiply by x, it becomes n minus 1 now. Okay, because you multiply by x term. And then from the next one, we can bring the x inside. So if you bring the x inside, it's going to be sigma n going from 1 to infinity n cn x n. Why? Because you multiply by extra x. So n minus 1 become n. And then the last term, what's the last term? Sigma n going from 0 to infinity cn xn equal 0. So to get now, so we substitute and bring the x outside x term inside. That's the next one. Now what we're gonna do, we're gonna see what are the starting terms. So that's what we check. So let's check the starting term. If you apply n equal 2, the starting term is x to the 0. If you apply n equal 2, starting term is x to the 1. Okay, so that's slightly different. Again, in the next one, if you apply n equal 1, starting term is x to the 1. The last one, x to the 0. So that means there are uncommon terms, because in the first one, the last one, there's x0 term that is uncommon, because the other two series does not have that term. So what we can do, we can write the uncommon terms first. So let's try the two uncommon terms. There's a one uncommon. After that, if you start with the next index, that means n equal 3, you can see that you get x1. In the last one also, if you start with n equal 1, you get x to the 1. And everything have x1, 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 x1 on all four. So that means they have common index. So we only write the uncommon index. So uncommon terms. So what are the uncommon terms? You get uncommon term of the first one when you apply n equal 2. So that means it is negative 2 minus 1 c2 x to the 0. So that is the uncommon term. From the last one, for the last term, you also get uncommon term when you apply n equals 0. So we write that. And then what we can do, we're going to write the rest of the terms using the proper index. So in the first one, now you can see that n equal 2 we already plug in. So we apply n equal 3 now. Okay, because for the first one we already wrote. So minus n minus 1 cn x n minus 2. No change, just the index. Just the index. The next term, no change, because it's only for the uncommon term, so no changes here. Yeah, there's a lot of writing. I don't know whether even enough space here. And then I'm going to write here negative, no change, because still this is a common term. So we can write n cn x to the n. From the last one, it has to start with n equal not 0 but 1. because we already wrote the first term there. So that is what we do next. So we change the indexes only for those uncommon terms. Now what we're gonna do, we're gonna use the seesaw method now. We're gonna reindex now. We're gonna reindex and see whether we can bring everything into one common index. That's very easy to do. So let's look at the terms now. You can see we need to bring it to xn if possible. So how to do that? We're gonna bring this one by up by 1, this one down by 1. So then it's gonna be xn, power xn. Here you can see you want to bring this one up by 2. So this one down by 2. And then everything else in xn, so fine. So we only need to change the index of 2, just 2 series. So let's do that. So we're gonna get, after we reindex, so we're gonna get, so we're gonna start with the first one, and then only the first two, and then we have the other two. We can combine them also, because you can see the last two you can actually combine them into one. So let's do that. So we're gonna get, so we have this now. So we have negative 2 C2 plus C0, we have that, and then we're going to use the seesaw method for reindexing. We're going to bring it down by 1, down by 2, so it's become n equal 1, because we had n equal 3 before, it became 1, infinity, no change. Now inside you're going to increase everything by 2, so you add 2, outside you subtract 2, inside you add 2, because n become n plus 2, n minus 1 become n plus 1, c n become n plus 2, x n minus 1 become xn plus, let's go to the next term. In the next term, we need to bring it down by 1, so it's become n going from 1 to infinity, so you add 1, become n plus 1, and then we have n minus 1, that become n, this is c, become n plus 1, and then we have xn minus 1, that become xn. And what we can do with the last two, we can actually combine them into one, because you can see they are the same, so we can combine them. So we have, so if you want we can just leave it, because just to keep the argument. So we have n going from 1 to infinity, n cn xn, and the last term is n going from 0 to, not 0, it's again 1 to infinity. So 1 to infinity, we have cn xn equals 0. Now what you notice that everything has the exact same index, n1, 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 n1. Also everything has the exact same power. So what does that mean? You can combine them. So we're going to combine them. So let's combine them. So once you combine, you're going to get negative 2c2 plus c0. Now let's combine. Let's write the common index outside. So the common index is n going from 1 to infinity. That's the common index. And let's put those terms together. From the first one, you're going to get negative n plus 2, n plus 1, c n plus 2. That's the first one. And from the second one, you're going to get plus n plus 1, c n plus 1. And if you combine the next two, you can see one has a negative n cn, the other one has cn. So you can see, you can write this one as, if you order the plus sign, it is 1 minus n cn. You can write it like that, because one has a negative n cn, the other one has a cn, so we can write it like that, and then write the xn power outside, which is whole thing equals to 0. Now again, if this whole thing equals 0, what we're going to do, we're going to equate the coefficients of each term, each linearly independent term. So you can see that that implies that, the first thing implies that is this has to be 0. Other thing is that this term has to be 0. So that's what you get. So let's put those two together. Let's set them equal to 0. So if you set the first one equal to 0, so you're gonna get, you can solve for C2. You can see that the C2 equal 1/2 C0. That's what you get. If you set this equal to 0 and solve for C2, you get that. And from the second one, if you solve for Cn plus 2, so I'm going to solve it here. So if you solve for Cn plus 2, just set this equal to 0 and solve for Cn plus 2. So you're going to get simply n plus 2 equal, you can see n plus 1 term get cancelled from the first two terms. So you get n over n plus 2 Cn plus 1 minus, and then you're going to get n minus 1. I put the minus 1 outside, it's easy. And then we have here, we have n plus 1 over n plus 2. So n plus 1, n plus 2, Cn. So that's what you get, okay? And this is valid for n going from, what is the index value? 1. So starting with 1. So 1, 2, 3. You can see that's the exact same indexing value here. See, that's the starting. Okay, so that's a relation. So that means we know the relation. So what we can do is we can calculate few. We can start plugging the values and then try to calculate a few of the terms. So let's do that. Okay, so after that, after you get the relation, we can start calculating values. So we can start with the first indexing value, n equal 1. If you plug n equal 1, you're going to get C3. So let's plug in. So if I n equal 1, what will happen is a 1, and then over n plus 2, that means 3. Cn plus 1, that means C2 minus. If you apply n equal 1, what will happen? N minus 1 becomes 0. So you get 0 times C1. 0 times C1. That means C1 disappear. It's 0 times. Okay, so that's what you get. So in other words, now what we're going to do, we're going to substitute for C2, because C2 we already know from the previous step. See, C2 equal 1/2 C0. So let's plug in there. Since plug in there, you get 1 over 3, 1 over 2 C0. In other words, you're going to see that later it is factorial 3 C0. Factorial 3 means what? What is factorial 3? Factorial 3 means 3 times 2 times 1. So you're going to see that going to appear here. Okay, but if you don't see it, that's okay. When you write few more terms, you're going to see that. Now let's try to calculate the next term. So we're going to calculate n equal 2. So by n equal 2, this becomes C4. So let's plug n equal 2 in the equation. It's a 2 over, nope, it's a 2 over. So it is 2 over, so when you plug in 2, it becomes 4. C3, actually I don't want to write that large. So it is 2 over, man. So it is 2 over 4 C3, and then minus, if n equal 2, that means for 1 over, what do you get here? When you apply n equal 2 to the equation, you're going to get 3 times 4, so 4 times 3 C2. So that's what you get. Now what we're going to do, we're going to plug into C2 and C3, both of them. So let's plug in. So if you plug in, what do you get? From the first one, you get 2 over 4 C3. What is C3? It is factorial 3 C0 minus 1 over 4 times 3, plug into C2. C2 is 1/2 C0. Now you can see that they have the exact same denominator. That means they have the exact same factorial 4. And then in the top, it is 2 minus 1. 2 minus 1 means 1. So that means it nicely simplifies to factorial 4 C0. That's interesting. Do the same thing. N equal 3. Let's choose one more. Then you can see it's clear. So you're going to get 3 over 5 C4 minus 1 over, if I n equal 3, so it's going to be 5 times 4 C3. So let's plug in here. So you get 3 fifth C4 means factorial 4 C0 minus 5 4 C3. C3 means factorial 3 C0. The same argument, you can see the denominator is simply factorial 5 now. And the top is 2 minus 1 again. So that means is that right? Yeah, actually there are some typos here. So it is not 2, this is 3, and also this is not 1 anymore. So this is 3, so 3 over 5, and then here it is, you plug in n equal 3, this becomes 2. You have 2 divided by 5/4, because n minus 1. And you can see now it's again simplifies very well, same denominator. The top is 3 minus 2, that means 1. So it's going to be 1 over factorial 5 C0. So that means you can guess what's going to happen with for Cn. Cn has to be 1 over n factorial C0. So in general, so that's why. So once you write few terms, you're going to see a pattern. Okay. So try to find the pattern. You just write few terms until you see a pattern. Or if it's a difficult problem, what's going to happen? The problem will ask you to write just the first 5 terms, or like 4 terms, 5 terms, like that, if it's a difficult one. But if it is like this problem, very nice, you can solve them. You can simply go forward and find them. Okay, so it depends on the problem. It's a difficult one, just like few terms is enough. Okay, so let's now, you can see in general. Okay, in general, you can write Cn, which is 1 over factorial n C0, which is valid n going from, so what's the starting value? We can start with n equal 3, right? Yeah, because we apply n equal 1, but we start with C3, so that means starting with 3. So 3, 4, 5, like that. But we also know that, and we know that C2 is 1/2 C0. See, fortunately, that also the exact same format. So that means we can simply write this one as Cn is factorial 5, factorial n C0 for n going from 2, starting with 2, not just 3, because it has the exact same format. You see, this is the exact same format. Good. So that means now we know the general form. So let's plug in. Okay. So we can substitute that in the equation. So substitute. So when you substitute, is y, which is C. So let's write the formula. So this is the sigma notation. So we're gonna plug in that. So n going from 0 to infinity, Cn xn, so which is C0 plus C1x plus C2x squared, like that. So let's plug in here. So when you plug in, what do you get? So you're gonna get, we like C0 we leave, C1 we don't get from here, so we can leave that. And then starting with C2, we have a formula. So it is 1 over factorial 2x squared, 1 over factorial 3x cubed, like that. Actually, and also we forget the C0 term, so let's write that. So I'm gonna, yeah, you can put that top. So this is C0. There's a C0 term everywhere. With C0 times. Okay, so you can see, so that is the case. Now what I'm gonna do, you may or may not see a pattern here. The only thing missing here is the C0 term for the x to the first power. So what we're gonna do is, we can write like this now. We can write this one as, I'm gonna add and subtract that term. So, so what we can do, I'm going to add and subtract. So we can write C1 minus C0 x, that's the first term, x1 term. And from the rest, I'm going to add here, the C0 coming here, that's that C0 term. So I'm going to write the rest. So here, we can add the C0 term. So this is a C0 x term, that's the one I add. So this is subtract, I add. So add and subtract. Now write the rest, just write the rest. So what's the rest? c naught over 2 factorial x squared, c naught over 3 factorial x cubed, like that. And you can see from the rest, so this c1, c naught, it's just a constant. I'm going to say it's a big c1 plus, what's going to happen here? Here we have this c naught term. So you can pull the c naught out. So if you pull the c naught out, it's just like just a term. So what do you get? You get 1 plus x plus 2 factorial x squared plus 3 factorial x cubed plus, like that. This is simply the e to the x. So that means you're going to get this c1 is not the c1. This c1 is simply equal to c1 minus c0. So it's just a number. That number I call c1, the big c1. So we're going to get c1x plus c0 e to the x. So that is the solution of the differential equation. It's very well simplified, and sometimes this happen, you can do that, but not always. So this is the kind of thing, but in a final exam, this may not be possible unless it is like a short problem. The first problem is okay, but you will get a manageable problem. But this is like a little long, unless you can do it really, really fast. But in exam, we don't expect that because you have a lot of things to do. So, but what I'm going to show you how it works. Okay, this is how it works. Sometimes it works very well. So you will get something manageable. Okay, not like this long. So you can look at the problem that you get for exam 1, things like that. Okay, good. So that is the power series method, and you can like do any problem like that. So it's not difficult, but you can see it's like a simple thing. So next we're gonna do is we're gonna talk about Laplace transform method. So let's talk about the Laplace transform method. So it's number 24, the Laplace transform method. Laplace transform method. So this is again a very powerful technique. You can do a lot of problems using this technique, because we know that we get stuck when you try to find the solution with undetermined coefficient method, because there are only three problems that we can do, 3 type of problems that we can do. And then also, if you try to do the variation parameters, you get an integral that may be impossible to get the closed form solution. Then we have this new technique, what we call the Laplace transform method. So let's try to look at the definition of Laplace transform. So the definition, let's say you have a function. So for a piecewise continuous and exponential order function, for a piecewise continuous and exponential order. That means it's going to grow slower than an exponential function. That's exponential order functions, or at least at the level of at most at the level of exponential function, linear exponential function. So that's what we call exponential order. It doesn't grow faster than that. So piecewise continuous and exponential order function, exponential order. Okay, so that means it's slower than e to a k t function, slower than that. Maximum is like that. Exponential order function f. The Laplace transform is defined to be the Laplace transform is defined to be, we're going to use this notation, curly L, f equal, it is from 0 to infinity e to the minus st ft dt. So you get you integrate with respect to t, and the limits going from 0 to infinity. We write this one as fs, because once you integrate, you get the function of s. So we write it like that. So we use uppercase f for that. So that is the definition of a Laplace transform. Okay, just an improper integral. You learn improper integrals in Calc 2, so we use those ideas. Okay, so let's use the definition to find a Laplace transform. It's just a simple function. So let's say example, find the Laplace transform of, let's say, 2t minus 3. Just use the definition to see how it works. So the Laplace transform of 2t minus 3 is, by the definition, 0 to infinity 2t minus 3 times e to the minus st dt. You can see this is a good candidate for integration by parts. So let's do that. So I'm going to use a regular technique. You can use the DI method, no problem. So if you use a regular technique, u has to be 2t minus 3. dv is negative e to the negative st dt. We take the derivative of this one, so du equal 2 dt. We take the integral of this one as a parameter, is act as a constant. So it is e to the minus st divided by minus s, because you divide by the constant term. That's how you integrate a exponential function. That's a constant, you divide by that. Okay, so we have that. Let's plug in here. So if you plug in, you're gonna get so it's a uv minus vdu. So uv, so it is 2t minus 3, that's a u. V is e to the minus st over minus s, in limit going from infinity to 0. And then so uv minus vdu, minus, but there's a minus sign there, so it's become plus. There's a 2, I'm going to write the 2 outside. So so vdu, so you can see the first product is the top row, that's the integral is the top row, the other one is the bottom row, you can see. So that's the bottom row we get. Now we are going to writing, so it's 0 to infinity, the bottom row. So let's try the bottom row. I need some space here. So so let's try the bottom row. What's the bottom row? It is so with a minus sign, so it becomes plus 2. So we multiply this, so I write s outside, so you only have negative st dt. That's the bottom row. Top row is the integral, bottom row is the second integral here. That's how you remember the integration by parts. Okay, now you can see, let's plug in here. So if you plug in infinity, now there are some problems, because you see that one goes to infinity, one goes to 0, one goes to infinity, because the polynomial goes to infinity, e to the minus st goes to 0. So that means indeterminate situation, so you have to use the L'Hopital's rule. But there is a small result that you can remember. When you try to compare with the exponential function always win. So that means whatever happened to the exponential function, everything happened, the whole thing, the same thing happened to everything. So in this case, exponential part goes to 0. That means the product has to go to 0. So that's the result. When you have an exponential function and a polynomial, exponential function wins. Okay. So whatever happened to the exponential function, the same thing happened in the product. So that means when you plug in infinity, it's 0. Okay. So you get 0 when you plug in infinity. Now, when you plug in 0, because this is the we will plug in for t. So when you plug in 0 for t, so you're gonna get so t term is gone, so e to the 0 is gone, is 1. So you have 3 over s, but there are 2 negative sign, and also there's a negative sign coming from the, when you subtract, there's another negative sign, that means there are 3 negative signs, so you get negative 3 over s when you plug in 0. Okay, now the next one. Next one, what we can do, you need to integrate that. So if you integrate, what will happen? So you have plus 2 over s. When you integrate, you're going to get one more negative sign. So that means it's going to be 1 over negative s e to the negative st, the limit infinity and 0. The same argument. When you plug in infinity, it is gone. When you plug in 0 for t, so it's 1. With the negative sign, it's become plus. So that means you end up getting 2 over s squared minus 3 over s. So that's what you get when you finish the integral, and you can see that's not that difficult. So this is just use the definition to get this one. Okay, so what's going to happen, we are not going to do that like every time when you get this one we use the table. So let's look at the few common values that you want to remember, and in the exam you will get the table. Okay, so you get a table that you used before. So these are the common ones. So